Hey everybody, so in today's video we're going to go through several examples of space-time diagrams. Now a lot of these space-time diagrams are from examples that we've already done in class with Lorentz transformations. And so the hope is that we'll be able to go through the space-time diagram and be able to show you visually the same thing that we saw when we went through the Lorentz transformations. All right, so we're going to go ahead and start with one of the first ones that we did, which was this. We have two trees, right? And standing in the middle, and lightning strikes both of those trees at exactly the same moment, right? At least that's kind of lightning. At least as far as this guy is concerned, it's at the same moment. So if I were to draw a space-time diagram for this, okay, I would have my y-axis, but my y-axis, remember, is not y, it is ct, right? So that's the time axis. We are multiplying it by c for reasons that we've seen, and hopefully we'll see more reasons for that as we go through, but either way, that is the norm, all right? Now, we're going to create our y-axis here. The y-axis represents position, right? Now, remember, all of the examples that we're using are all going to be basically one-dimensional in nature. We're not going to have any 2- or 3-dimensional problems here, all right? So, as we go through this, we see one lightning bolt hit right here at the fir tree, at the pine tree, and then we have one lightning bolt strike right here at the oak tree. Now, you'll notice that I put both of those on the x-axis, right? So on the x-axis, that means that time is 0. And so that is at time 0, we see both of these things happening at time 0, just at different locations. One over here and one over here. All right? Now, the next thing that we said is, well, what if we have a guy here in a rocket ship that is flying with velocity v towards the pine tree? What is he going to see? All right, or what is she going to see? All right, so for that, we're going to create our new world line. Remember that a world line with a slope of 1 represents the speed of light when we have c here. And so I don't want it to be 45 degrees. Okay, I'll have it be something slightly different. Okay, so this is going to be the world line for CT prime. So this is my S. This was my S prime, right, in the original question. So my S prime creates this world line of CT prime. Now, remember that as we do this, not only is the time axis going to change, but whatever this angle is right here, then the x-axis, the position space axis, that's going to change as well, because we have to make sure that the distance from here to my slope of 1 line, the speed of light, is the same as the distance from my x prime to the speed of light. That will make sure that the speed of light is the same from any perspective. Now remember, what I'm doing as I do this is I'm actually just creating a new x and y axis, right? So hopefully that's pretty close. It may or may not be perfect, but you get the idea. This angle right here has to be the same as that one. That way my 45-degree angle, or my slope of 1 here, ends up giving me exactly the same thing on both sides, okay? So from this, I now need to find out where and when did that point happen, this striking of the fir tree. Now, we know from our example before that the spaceship moving towards the pine tree should see that happen first. Okay, so we're expecting an earlier time here. So remember that this essentially has created a new XY plane. So we have our grid lines that are kind of going up and down like this. Yeah, I know they're not perfectly straight. And then for this, we have our grid lines that are going kind of this way, right? That's our new coordinate plane based off of our new X and Y axis, our new world line, right? So for that, if I want to figure out at what position this occurred, then I need to follow these lines parallel to the y-axis until I reach my x prime. So I'm going to keep this parallel as best as I can, and what we'll see is this right here. And so this is the location, the x prime, that's what he's going to see. All right? Now at the same time, we also want to see the time at which that occurred. Again, from this point, I need to follow along my x-axis until I get to my time axis to be able to read that point off. Okay? This shouldn't be surprising when we have x and y axes before. If I have a point, to get the x value of that point, I follow the y, right? These y grid lines parallel to the y-axis, and that gives me the x value of that point. If I want the y value, then I have to follow the grid lines in the parallel to the x direction, and that will give me the y value of my point, right? And so again, if I want the time, the y-axis, then I need to follow my horizontal grid lines. And so my horizontal grid lines look like this. So what you'll notice is that it's actually going to end up being down here so that it's parallel to that axis, down below the x prime, which is negative. So I'm actually going to need to extend my CT a little bit. So we're just going to extend this out this way. And hopefully what then we'll see is that as I go parallel to that right there, we will get right there, that would be the point on the CT prime. So this is the T prime for the fir tree. And you'll notice that it's negative, it's before time 0. Remember, this guy saw them happen at time 0. This person will see the fir tree happening before that because he's moving towards the fir tree. Now, if we want to do the same thing for the oak tree, then we'll be able to figure out at what time the spaceship saw that. And remember, this one was seen later because we're moving after. Okay? So again, if I go parallel to my x-axis, right, I need to continue to be parallel just like that, but I'm going to go from the point on my grid right here. So, oops, right there until I get to the y-axis, and therefore here, that is the time at which the spaceship will observe this event happening, this time right here. The location, of course, we would have to extend the location line here, the space line, and then from there, I would go parallel to this line, like that. Oops, I think that's still more or less parallel. And that right there would be the x prime, the position, all right? So hopefully that kind of makes sense. That does kind of connect with what we saw before, where the spaceship sees this one happening before it sees that one, all right? So there you go. There's our first example. All right, I'm going to go ahead and erase this one. We'll put up another one that's similar to another example that we saw in class. In the next one, you may remember we did an example about two people that are observing two claps. These claps occur at the same location. It could be claps, it could be flashes, whatever it is. These two happen at the same location. But one happens at T1, the other happens at T2. All right? So if we draw our coordinate plane for S, that will be just our normal. We'll have CT, and then we'll have our x-axis here, which is x. Okay, notice that I didn't need the right and left this time because both events are happening over to the right. Okay, now I can draw the events. Okay, the first event is going to happen at T1, the second at T2, but they're both going to happen, according to S, they're both going to happen at the same X. So I'm just going to choose a random X. I'm going to say that they happen at this position. Okay, and then I can put a T1 right there, and I can put a T2 vertical of that. So this is my T1, This is my t2. Recognize to get the time, I would just go straight from here over to the y-axis. I can get the time from that. I can go from straight here over the y-axis. I can get the time from that. So this represents two events happening at different times at the same location. All right? Now, with that, we can now look at what would happen from the perspective of the moving person. Okay, the moving person, again, is going to have a different world line, so we're going to add in their velocity. Okay, so something like this. So c t prime. So that's what they're going to, that's their motion from the perspective of s, right? They're moving with some velocity to the right. Okay, again, because I have a ct prime, I should also have a similar x prime here. All right, so I'll go ahead and draw that in. All right. Now, with that, I should now be able to see what is seen by the s prime. Okay, so if I look at my first point here, okay, my first point, to get the position, I'm going to create a line like that. Okay, parallel to this one, that will give me the x prime 1. Okay, so at a very similar distance. Okay, and then to get the time, I need to go parallel to the x-axis. So he's going to see it at this time, right? So position fairly close. The time, notice that the time is lower on my y-axis, which means that he is going to see the first clap before the s frame of reference sees that, okay? If we look at time 2, we can do the same thing. So again, to get the position, the distance between s prime and that one, we'll go parallel to the CT graph. So we look for that axis, that coordinate plane right there. And we go like that. And we see that it happens here. Notice that this is shorter than the original one. That should make sense. He's moving towards it, so therefore when the second one occurs, he should be closer, right? Remember, x prime is the distance from s prime to the event. From his perspective, the events are actually moving towards him. And so when time 2 happens, when the second event happens, it will be closer to my s prime frame of reference. Now to get the time for that, again, we'll take our x prime graph, we'll keep parallel to that, and we'll go like this. Oops, that didn't work as well as I hoped. There we go. And so that right there would be t2 prime. And again, you'll notice that that happens sooner than this one. Okay? Now, one of the things hopefully you're noticing is that if this is not very steep, then this is not very steep, and it doesn't change things very much. The more that this kind of leans over this way, the more that this will lean up, and the more that things will be affected. Okay? The closer we get to the speed of light, the more that our results will be affected in the long run. Okay? If we are very, very close to the worldview of S, then things will change very little, if at all. And that's why when we do Newtonian mechanics, we don't really have to worry about Lorentz transformations and space-time diagrams and things like that, because if this is really, really steep, close to the CT, then there's basically no difference between the times and no difference between the distances. It's only as this becomes closer and closer to that slope of 1 that we start to get some significant differences. But do note that what we see here is that it will happen sooner it will be closer. All right? Hopefully that makes sense. Let's move on to another example. So here's the next one. We've seen this one before as well. Remember, we had one guy that was stationary. We had one guy that was inside of a spaceship moving. And then we have a rod which is inside that spaceship. Okay? The spaceship is moving with a velocity v. And so therefore, we have some interesting things happening. Now, what you might remember is that we have something called length contraction. Okay, which means that for the moving person, it will be a different length than for the person who is stationary. All right, so let's have a look at this. Let's see what happens. Okay, so we understand that proper length is measured by the S prime here, right? He's the one that's going to be able to measure the length properly because he is moving with the same velocity as the length. Okay, however, what we are going to do is we're going to be looking at this from the perspective of S. Okay, so once again, let's get our coordinate plane up here. Okay, so this is our CT, and this is our X. Okay, now given that, we now have S prime. So S prime is going to have its world line here. Okay, we'll make this one a little bit steeper just for the heck of it. Okay, so CT prime. Again, with that angle, I'm going to need essentially the same thing down here. Shooting for about the same angle. I guess if I go like this, I should be able to go like that. So maybe something about like there. Okay, so that's my X prime. Hopefully those two angles are more or less the same. Remember, the angle is important because the tangent of the angle is equal to V over C. We did learn that. That's one of the things that's in your data booklet, so we can use that. Okay, so there we go. Now, how about the rod? Okay, now one way to do this is just to say I'm going to define this point right here as being X prime 0. All right, so this is my 0. That means the person is a little bit to the left, so the person would be over here. If I wanted to draw the person in, I could, right? The person's moving at the same velocity, so they would have a parallel world line. So the person would look like this. All right. So that would be the world line of the person moving parallel to the rod. Okay, but because I made the left side of the rod be my 0, then my X prime 0 is going to be here. The right side of the rod, I'm going to create another world line for. So the right side of the rod, I'm just going to kind of draw a second world line, kind of like this. Okay, so that is the right side of my rod. And so for the person inside of the spaceship, they would measure a specific length, right? They would measure something like this. They would measure this right here. Okay, this right here would be L prime. That's the length in this reference frame, right? The rod would go from the left side over to the right side. So they would measure this length right here, from the left of the rod to the right of the rod. That is the perspective of the X prime. Okay? Now, what would the person outside of the spaceship see? Okay, well, they would see these two locations, these two events, right? This is one event, this is the other event, one side of the rod, one of the other side of the rod. So they would see those two things, but they would see them slightly differently. Okay, we have to then, from this point, to find the length that the S sees, we would go from here straight to there, and they would see this position right here. That would be the right side of the rod. The left side of the rod would be right here, so XL. So notice what the person S would see is they would see this length right here. Now, we know that the hypotenuse is longer than the side. And so therefore we can see that L prime is longer than L, which that is what we said. We said that when an object is moving, that the stationary person will see it as being shorter. That's what we call length contraction. The person in our inertial frame of reference here will always see a moving object as being shorter than a stationary object. For this person, L is stationary, so they see the proper length, the normal length. Okay? Now this can be extended in any number of ways, right? You can say, well, what if we wanted to look at the length of the rod at some later point? Well, if I look at the rod here, the rod would go from here, parallel to the X, right? That would be the length of the rod, according to S prime. Okay, you don't go this way because my x-axis goes that way. So they see both of these at the same point. Then, if I were to go down, you see that right here, you'd get exactly the same thing. You would get that same from here to there, and that would give you L, the length which is being seen by the person on the outside. Okay, so this again is an example of length contraction, and so we can see how the lengths work. Exactly the same as what we saw when we did our Lorentz transformations. Okay? All right, let's do another one. So here's our last example, because I want to show you what light looks like when we start looking at light and how that travels in our space-time diagram. Okay, so what we have here is a series of beacons, maybe as you're approaching a planet or as you're leaving a planet, that kind of help the spaceship know what direction it's traveling, how far it is, you know, and kind of direct the spaceship as it's leaving or landing. Kind of like buoys in a seaport, right? And so what we have here is 4 different beacons. You can see that they're located in different places. Now remember, this is in a straight line, right? So we have some that are over to the right. We have some that are over to the left. And so the question then is, when do people see these things happening? Okay? So first we have a guy that's stationary. So we have a guy that's stationary at 0. When is he going to see these things happen? Well, if we go with his viewpoint here, okay, this is the viewpoint of my S, okay, my guy that's stationary, then what that person will see is just according to the CT, right? You can see that W and Z, both of those happen at the same time, right? So S would see W and Z at the same time. Then moving up the time axis, they would see X. So then they would see X. And then last of all, they would see Y here, right? And so we're just following along the axis and we're seeing what happens as time passes. Okay, even though they're in different places, the different locations is represented by this, the different times is represented by this, all right? So now what we want to do is we want to say, well, what would happen if somebody was in a rocket ship that was moving to the right, okay? So if we add that in, so let's add in our spaceship here. there is our spaceship, so that's our CT prime. Okay, what are they going to see? All right, so in order to do this, we actually have to look at how the light is traveling, because this is something different. This is a separate situation, right? We have the light that is moving at the same time as this is moving and this is stationary. Okay, now I'm not going to draw in my x prime here. I could, but it's not really important to the question because the question is about time. Okay, so I'm not going to worry about that right now. What I'm going to do is I'm going to draw in the world lines for the photons. Now, this part can be a little bit confusing. It threw me for a loop the first time. So we do know that the slope should be 1. Okay, so from here, I should have a slope of 1, something like this, going up in that direction, right? So a little bit less steep than this one, but slope of 1, 45 degrees that way. Now that's going to the right. If I'm going to the left, I don't want it to go down this way because that would show that I'm going back in time as the light moves to the left. I want to be able to show that the light is moving to the right and to the left, but that time is progressing in the forward direction. So in order to do that, light, photons, are going to have a second line just like that. So this one is representing the light that's moving to the right. This one is representing light moving to the left. Okay? Both of those have a slope of 1. Okay? This one is -1, that one's +1, but they both have that slope of 1 to represent the speed of light. Okay? So what we see is where this contacts the world line for CT prime. So that means this is the time at which the moving spaceship will see Z occur. We can now do the same thing for all of them, right? I can go, hopefully, more or less parallel to this one. They should all be basically the same like that. So this guy can go up like that. This one, something like this. Oops. And then this one, parallel to that. Something like that. And then from the other direction, you should have 45 degrees, slope of 1 in the other direction. So like that, and like that. Okay, so you'll notice that each one has light going to the right and light to the left. Obviously, not both of those are important. I could have just drawn one, but I wanted to make sure to show you that the light has to travel in both directions. Now, what about the time? Okay, well, we see that Z happens first. That's the lowest on my time on the world line, right? The next one would be Y here. So the V would see Z first, then it would see Y, then it would see X. That would be the next one to hit my world line here. Oops. And then it would see W last, but not least. All right, so I wanted to show that to you so you can see the photon world lines, okay, because it can be confusing, not just going like this, but it also needs to travel back in the other direction. And secondly, to kind of look at what would it look like if we had multiple events happening at the same time, and how would we interpret those on our world line. We can see where they connect with our world line, and so we can see when that observer would then see those things happening. Okay? So I hope that was helpful. I hope that those examples have helped clarify how we might use this a little bit. The hope is that over the next day that you'll be able to practice these a little bit and be able to make some sense out of some different situations. Obviously, they could give you something exactly like one of these, but they could give you something slightly different as well. So hopefully you'll be able to kind of play around with these and make some sense, and that it'll work for you, all right? So we'll see you next time. Let me know if you have any questions.